This bridge behind me may not look that remarkable as an old railway bridge, and for all I know, there's nothing all that special about it, but there's a couple interesting things that I've noticed, and I thought I'd show you. This bridges the Lamoille River in Wolcott, Vermont, on what is now the Lamoille Valley Rail Trail, but it's had a couple different names in the past. When the state took it over from the 70s and continued running trains till the 90s, um, it was called the Lamoille Valley Railroad, and before that, it was the St. Johnsbury and Lake Champlain Railroad, which is what it was at the time when this was built in 1928. Now, certainly being built in 1928 isn't unusual for bridges in Vermont. And that's because the previous year, November 3rd and 4th of 1927, there was a major flooding event in Vermont known as the 27 flood. It really is the state's biggest flood, though in certain areas of the state, more recent floods have had larger flows. But as a statewide event, it was probably the most disastrous flood that the state has seen. Many road bridges in this town of Wolcott were washed out in the 27 flood, two of which I know were rebuilt in 1928. One crossing the Lamoille River still stands, though it has been deemed structurally deficient enough that a temporary bridge was put over it a few years ago. The other, closed for many years due to structural deficiencies, was removed in 2020, and no longer carried an important enough road to keep it around. And aside, at the location of this removed bridge, it looks like the old bridge, the previous one, when it was removed or washed out in 1927, looks like it just dropped down and was left in the river these going over 90 years. I'm sure that this isn't the recent bridge that was removed, both because I know it didn't have the concrete handrails or the guardrails that this one has, and there's no way it would be environmentally allowed nowadays. But they just left it in there after it got destroyed in 1927, though to some degree it might be allowed nowadays during a major flood event. This bridge was rebuilt in 1928, but the original bridge here was built sometime between 1869 and 1877 when this rail line was constructed. So the November 3rd and 4th flood caused really quite massive devastation. On this rail line between St. Johnsbury and Swanton, there were about 160 washouts, 12 bridges, 6 culverts, and 24 landslides wrought havoc with the line. Though there wasn't any damage to the rolling stock or the buildings, unlike some areas in the state where the rail yards were in the flooding zones and there was quite a bit of damage. It's pretty impressive that they're able to get parts of this line running by November 18th, the two ends of it between East Hardwick and St. Johnsbury and between Cambridge Junction and Swanton, which tells you that where we are now, which is between Hardwick and Cambridge, really was the area that took the worst of the damage along the Lamoille River, as opposed to where the railroad on those other sections actually goes out of the Lamoille River watershed. But this section was opened by Christmas Eve of that same year, which means that they'd put a temporary bridge in here or fixed up the old one enough to get trains across prior to rebuilding this one the next year. Throughout its history, this rail line has been plagued by numerous washouts and bridges being taken out. Just upstream of this location, the next bridge on the rail line over the tributary Wild Branch washed out in 2000. Well, actually, from this photo, the fate of the bridge is unclear, but the material behind the abutment washed out and the bridge was at least no longer serviceable. In the 1990s, prior to this washout, the state stopped running trains on this line due to shifts in freight demand and the numerous washouts on the line. Washouts have continued. Just a little ways upstream, even before that bridge, there's a big section that they've had to put stone and riprap in to prevent the river from eating away at this embankment as they convert it into a rail trail. And there's numerous other places along here where they've had to do pretty major reconstructions, including actually up at the bridge over the Wild Branch that had washed out. They've, in the October or Halloween storm, though it mostly happened November 1st of 2019, that had a big washout, and they had to put in a lot more stone in that location in preparation for, I guess, rebuilding a bridge across there as part of building this into the rail trail that is getting pretty close to completion. But none of those are the reasons that I first looked at this bridge. That has to do with something that, from what I've observed casually looking at bridges, is quite unusual. This bridge isn't, the abutments of this bridge aren't perpendicular with the line of the rail center line, which is actually fairly common among bridges. They're crossing a river at a pretty severe angle, and you don't want your abutments to kind of jut out into the river or come back too far, and keep your span as short as possible while still giving the river its space. But this does it in an unusual way. It's kind of hard to show you. I think a drone would help a lot, but I don't have one. But over here, you'll notice that the angles that are going up to the main area, they're different. Like the one further back is, one on the far side is shallower, where the one on this close side is a steeper angle. In fact, the one on the far side comes out about 26 feet, while this close one only comes out about 18.5 feet. And it's actually exactly the same dimensions on the other side, which means what I normally see in these situations as a parallelogram would work, whereas this bridge has the main section of the bridge, the pieces that go, the floor beams, and then the pieces that go across the top are perpendicular to the rails. They have the right angles from the main kind of girder sections of this truss bridge, so they aren't girders. Those center angles are about 23 feet. 23 foot 10 is what I could closest measure. So they're right, kind of splitting the end angles. These two trusses are the same. They're just not the same next to each other. They're flipped sideways. So that was actually what caught my eye on this bridge. And what I consider to be a more typical parallelogram angled abutment railroad bridge can be found downstream along the same rail trail in Johnson. The top members zigzag back and forth, forming one continuous chain, attaching at the locations that the vertical members come up to the top strand of the truss at. Due to the use of the Baltimore truss in this bridge, which in this angled formation has the shorter half-height verticals directly across from the full-height verticals, the floor beams are perpendicular, as we saw in the other bridge which used a Warren truss. I have seen other truss configurations used on angle abutment bridges, but I've not made a widespread enough analysis to see if the type of truss is strongly determinant on the way they're dealt with in terms of like what I call this parallelogram style bridge or any other type of bridge. Though I suspect that that would be the case because, well, perpendicular stuff is a lot easier to work with, and even if you have to do non-perpendicular stuff up on top with the zigzagging back and forth, if you can make your floor beams perpendicular, that would be, I imagine, quite a lot easier to work with than angled floor beams. When considering the restrictions that the parallelogram style bridge places on design, I can see many advantages to the first bridge I looked at when dealing with non-perpendicular crossings. In this bridge, the angle of the abutments are very much determined by, well, half the distance of one of the large triangles. You can't go longer or smaller without changing that large triangle length and still have this parallelogram bridge work. Whereas the previous bridge I was looking at, you can have shallower angles or angles of the non-perpendicular abutments because you're just working with kind of shifting the angles of those last pieces a little bit. But if you're using the exact same size of each of the members as I was seeing in that other bridge, you would have to oversize them in order to allow them to hold the same load of the maximum. Thus, that style bridge probably only works well at shallow angles, and therefore, if you need an angle that is as severe as, well, half the height or half the length of one of the triangles, this style of bridge would probably work better. And that may be why we don't see more of those, is because if you're working at those shallow angles of non-parallel abutments, why just don't make the abutments parallel? It might just be easier to make the abutments parallel than deal with uh, the issues of non-parallel abutments. The load of a crossing train is transferred from the rails to the bridge ties, which are perpendicular to the rails, to the stringers, which are parallel to the rails, to the floor beams, which are perpendicular to the rails, and then those transfer it onto the truss where the truss can accept load, which is at kind of each of the points. If you draw this as like a line diagram with each of these members just being a line, it's where those lines intercept that a truss can accept a load. Though no longer running trains, you can see that this system is still maintained with a plywood decking acting as the rails, transferring it to the replaced ties, which then continue that on down the line as was intended. Though for normal pedestrian traffic, the members, which are really only designed to work in tension or compression as two force members in the original design, could easily withstand just a couple people standing on them, though there is some heavier equipment running across this bridge. This is a finished portion of the rail trail, which the other bridge likely will be by the time I publish this video. This bridge has been finished for 6 years with safety improvements such as redecking and railings. Along both abutments, there's a number of these rather deep in some cases, in this case not so much, holes here. Now, I don't know what for certain caused these, but I have a suspicion. They definitely don't look like animal holes. And this bridge potentially was looked at for how good of a condition it was in prior to the reconstruction they were doing. And that might have involved some geotechnic investigations. And these look an awful lot like the size of boring holes. Now, I'd be surprised that they do 4 bores on one of these abutments. Like, this bridge isn't needing to be replaced. Like, I know the plans for rebuilding the rail trail don't involve replacing this bridge, but they probably wanted to check its condition. Now, most of those other ones I was looking at, I can't really get it with this camera, it just gets dark, look fairly shallow, 1 to 3 feet, whereas this one looks pretty deep. My guess is that when they're doing these, they're taking a boring and they ran into some rock that they really didn't want to have to drill through. So they just kind of kept moving back 10 feet each time until they found one that they could actually get a good boring in without running into rock. Because probably just made it easier. They knew they needed to get a certain depth, or I don't know, maybe they're going to bedrock. This end looks like the expansion joint end of the rail bridge, with those slotted holes, with the bolts in those slotted holes, which is a valid way of building expansion joints even on active railroads today. Though you might not choose to do it if you're building it new, but retrofitting an old bridge, I've seen it done with bolts in slotted holes. But they don't look all that good in terms of where they are. The other side looked like a fixed end to me. I didn't see any slots. But these look like they're basically all the way. They could maybe a little bit, the bridge all the way expanded. And today's not a warm day. It's in the 50s. So there can get a lot warmer days. Now, it could have been badly designed. This was built in rather hurry, probably in reconstruction, though not too much of a hurry, not immediately there. But I think it could also be that this abutment has shifted over time. The abutments don't look in great condition, with a lot of concrete peeling off, stones falling out, which for the age that these are and exposed to river, we know they're at least 92 years old, and the river washing by them, yeah, they're fairly typical of a number of other bridges I've seen, which they're also typical in the sense that they're entirely round stone, not a bit of angulated. Today, concrete, when you're pouring it, you'll use entirely angulated stone as the large aggregate, which helps it bind together and stay solid. But in this and a number of bridges I've seen built a couple of years before this one, 10 to 20 years before, this is actually pretty typical from what I've seen, using the round stone and quite large round stone rather than like 3/8, 3/4 inch stone, which I think would be typical of concrete today. And while this bridge was built in 1928, I'm not sure about the abutments. Even today, when abutments on a bridge are in good condition, but the superstructure isn't, it's not uncommon practice to just replace the superstructure and put the new superstructure on old abutments. It makes sense to do that, assuming the abutments are in good condition when you're doing a relatively fast rebuild of a bridge. But looking in another spot, there's this concrete is kind of coming off of, looks like a stone masonry part of the abutment, which could have been the older abutment, and they built this new abutment out further when they were building this bridge. The bridge looks quite well. These rivets here, they're pretty good condition. I haven't really seen any bad condition rivets on this entire bridge. These all look pretty well still functional and not even close to needing being replaced. Now, there's a couple reasons. It just could be that this is newer than some of the other bridges that I've seen rivets on that are in desperate need of being replaced. But that's not the only reason. This bridge is along the rail line, is several miles from the nearest paved road crossing, and even a pretty good distance from the nearest dirt road crossing. And what really attacks these rivets is the chlorides that come in road salt. That will just really eat away at the metal. So having a really good distance, and the snow, when the trains are pushing it along, back when this was a railroad, that snow with the chlorides in it can get pushed surprisingly far, is what I've been told by people who work at a railroad. And that will just eat it up. But if you've got a long way for that chloride contaminated snow to be pushed off, and instead of being pushed along as they plow the rails, it will get pushed off and not fall down and attack these rivets. It's also can help that there haven't been trains running over this bridge in over 25 years. So they wouldn't have even been plowing this. They'll run the groomer on it, which, yeah, does scoop snow up and deposit it in different places, but I don't know how much, but it just, in terms of how much that relates to plowing, but it's not too terribly recent that they last plowed this for the railroad. You'll notice that the main compression members running along the top strand of the bridge look substantially different than the main tension members running along the bottom strand. These bottom strand members are just in tension, so they're just being pulled apart, which means they, in theory, which not in practice, could be replaced by a cable. So they aren't going to buckle, which is the major failure point of tension members or compression members. The tension members don't buckle, whereas compression members can buckle, and that means you actually need quite a bit more material in steel when you're dealing with, or at least placed differently when you're dealing with a compression member to prevent it from buckling. A major advantage of a truss type bridge is that you can specifically design your members for tension or compression, because a truss, all the members are either solely in compression or tension, in like how trusses are ideally designed. Of course, there has to be some members like this floor beam that are in bending. As you see, it's kind of a girder design, but you can specialize your members, whereas other bridges that isn't possible. And there's a lot of advantages to trusses, but there's also a number of disadvantages, and you don't see them being built much any longer, which means that the disadvantages currently outweigh the advantages, whereas it used to be that the advantages outweigh the disadvantages. The number on screen will lead you to, in the description, will lead you to a website that kind of covers some of these advantages and disadvantages rather succinctly. These are also built out of a number of smaller members which were put together likely on site. This is something I have seen in a number of these older railroad bridges. I would guess just due to limited ability to move large pieces of steel into place. Where the rails were, up where my bike is quite a bit elevated above the valley floor that I and the camera are sitting on. In fact, the top of rail, it would have been just about 20 feet above today's water level, which is somewhat elevated given recent rain. Now, having the rail up that high has some advantages and disadvantages for flood survivability. One of the main advantages is that it doesn't get inundated as the floodwaters come, but I think it's actually put there not so much for the flood survivability, but just as it goes from valley wall to valley wall. It's just what it's doing in this particular area. But maybe there's some thought to flood survivability. It also could have been that as they're building up the embankment of the railroad, they just took whatever existing land was there and built up the amount of stone that they felt they needed to put in to provide a good base for the running the trains over. But in some areas of this particular railroad, they put it through what are farm fields, but floodplain farm fields. And in converting this to a rail trail, they've actually lowered those areas of the rail bed such that that floodplain behind the rail bed actually got reconnected. And so that the floodwaters can get into there and lessen the impacts of flooding. Actually, in the 1927 flood, the village of Bolton was actually pretty severely impacted when the rail embankment, which stood between it and the river, broke, and all this water suddenly came through that and flooded the town quite suddenly, as opposed to prior to that, it was acting as effectively a levee. The town was doing reasonably okay. So that it does certainly hold back floodwaters. One of the reasons that you won't see a ton of roads built like this, other than maybe the major highways that are a little bit higher up on the valley walls or just dipping through a valley, is that definitely for like local town roads, one of the ways that they try to design them, and even some state highways, I know that this is designed into them, such that the lowest point in the road approaching a bridge on one side or the other is lower than the bottom of the bridge, which means that water will start flowing over the road before it hits the bottom of the bridge, thus relieving the hydraulic pressure on that bridge, and the debris that's floating in the water won't crash into the bridge and potentially send it downstream. One of the things, this can be done on highways, car roadways, because you can dip it down and then bring it back up and cars can drive that, whereas railroads have to work at very shallow grade. So unless you have a really long area, that's just not practical to bring the level of the rail down so that water could flow over it and not get up to the level of the bridge first. While a bridge may be more resilient to minor damage than a roadway, it's a lot harder to rebuild. If a roadway washes out, if let's say the water goes over the roadway, washes out the roadway, that might take one or two machines in a couple of hours to put that back, whereas a bridge, even a temporary bridge, could take quite a lot longer, and permanent bridges would be much more expensive than just filling in a roadway and putting a new coat of pavement, or on a dirt road, just grading it out for a permanent fix. And temporary fix could really be quite quick. You just need to like run a bulldozer through it or something to make it passable for trucks. So that's a really good reason to lower it down, in addition to just reducing the height of floodwater in the surrounding area.